I love systems of equations. This is my favorite unit of the year.
Alright, how can graphs help you find the solution of two linear equations? We've looked at a couple graphs before that have two lines on it.
When you did that poster the other day, well, it's probably like a week or so ago, you compared, remember it was like the taxi service and the shuttle service, and you compared, and a lot of you saw the two relationships graphed together.
So how can they help you?
How do you find the solution on just one equation? Where's the solution of an equation if you're graphing it? Let's put together what we know about the graph of an equation and what the coordinates on that graph actually represent.
Maybe like your solution would be your y.
Be more specific, Leo.
Like the slope and your y-intercept.
Okay, we need more, a little bit more. Keep going.
Like the points on the graph kind of are your solution because your equation is finding the points on the graph.
So your coordinates, if you graph a line like that,
That's a line.
every single coordinate, whether they're the ones you can see or not, right? Because sometimes like those exact coordinates we see, but there's still little points in between. They are the solution for that equation. All of them.
So what if I graph another line and it kind of looks like this? It's illustrating.
What are the solutions of that line?
What are 2 points?
No,
One
what's the
is-
solution of just that line, the new one?
Just that line and like, all the points.
All the points on that line. Okay, so let's take it one step further. Is there any coordinate that is the solution for both lines?
Where it crosses, like that one where it crosses.
Yeah, this point right here, where the lines cross. That's a solution on both lines. Both lines have that coordinate as a solution. Alright, so a system of linear equations is two or more
Write this
related. Write this down. Is two or more related linear equations for which you're trying to find a common solution. So we just said that the common solution is where the lines cross. Where there's a point on both the lines, where they meet, that point is a solution for both lines.
And you'll do a lot of real world examples. Real world examples of this would be if I'm debating between two cell phone plans at Sprint and Verizon. Is there any amount of text messages where both would cost the same amount? Think about X would be the number of text messages, Y would be the total. Is there any point where both are the same? And when you compared with your posters that day, we actually got a really good glimpse into systems of equations because you all looked at one. These are better, like the real world scenarios are much simpler to understand than like the mathematical jargon. But we still start with this.
So in order to solve a system of equations, what do we need to find? What do we need to find in order to solve a system of equations?
What did we find on that graph? The one on the previous slide.
Yeah, the point where they both intersect. So the ordered pair or coordinate where the lines intersect.
So the value of X and the value of Y that satisfies both equations. Yes.
Alright. Okay. System of linear equations, two or more related linear equations for which we're trying to find a solution, a common solution. Solve the system of equations, you need to find the ordered pair, the point, and the coordinate that solve both equations in the system. So where the lines two equations, y equals 3x and y equals 3x minus 2. We're going to graph them. What do we need to know in order to graph these equations? Where they start, yeah. So
What would we
the
call that? The y.
y-intercept. So what's the y-intercept of the first one?
0.
0. Alright. And then what's the y-intercept of the second one?
-0.
Negative 2. Alright. And then what else do we need to know? The rate of change of the slope. What's the slope of the first one? 3. What's the slope of the second one? It's also 3. Alright, so let's go ahead and graph this. So for the first one, where are we starting?
Order.
0. The y-intercept when the line crosses the y-axis is at 0. Because our b would really be plus 0 here. And then where are we going from there?
X equals 1, y is 1.
Negative 2.
When x equals, say it again. When x equals.
1, y is 3.
X equals 1, y is 3.
Now, if you try to do rise over rod and make a mistake, the coordinate that you go to, use those values and plug them back into the equation to make sure you're correct. There's some confusion, and we know it's really common instead of like change in y or change in x to flip that by accident and do x over y instead. But whatever second coordinate you get, use those values and substitute them into the equation. You'll be able to prove if you're right or wrong.
Okay, so now we can draw a line here. Okay, the second one. Where's our y-intercept? What coordinate is our y-intercept going to be on? 0, negative 0, negative 2. Where are we going from there? Say it loud.
Go to the right 1 and up 3.
The right one, and then up.
Are you touching it? It's sensing the heat of your arm. So you hold the pen out farther.
Sorry. So the right one, and then up 3. The right one. Okay. Sorry, if these were straight lines, pretend that these are really straight. What do you notice?
They're parallel.
They're parallel. Good. Is there a solution for this system?
Why?
Why do you think that is?
Because they're going
I think that like since it's not gonna cross, like since they're parallel, they just gonna keep on straight.
Because the lines are parallel, they will never intersect.
So what about these equations make them parallel? If the line's parallel.
The y equals 3x. They both have it, so it's both going to start.
So they
It
both have
both has the same slope. It just
Same
starts
slope.
at different points.
Same slope. This is right downward.
same slope.
Different y.
Different y-intercept. So, and you all saw it right away. The same slope but a different y-intercept means the lines look identical but they're in different positions. So they're parallel, which means they'll never cross.
So they have. So what's their solution?
What's the solution here?
What's their solution?
Probably for the two lines, both of them combined, there's really no solution
No.
because none of them cross each other.
There is no solution.
So this system has no solution. We can tell right on the equation they have the same slope, different y-intercept. When we graph them, they're parallel. They never meet.
Think about if Miss K and I both have a job, we work at the same store, right? And every time she shows, like in the morning, she shows up to work, the boss gives her $10. Just, you're here, you get $10, and you're gonna make $5 an hour. And I show up, and the boss doesn't give me any money, and I make $5 an hour. Is there ever an amount of hours that will make the same amount of money?
No.
No. Because we both make the same amount every hour, but she gets 10 right away. So after the first hour, she has 15, I only have 5. After the second hour, I have 10, she has 20. We'll never, ever, ever intersect. Our costs, our money will never be the same.
All right. So everybody's got this right now. Okay. Oh, so this is what they look like when you actually graph them straight. Answer that.
Go.
Okay, so now let's take a look at this one. We have y equals negative 2x plus 3 and y equals x plus 3. Someone help me out. How do I graph that first one? Okay.
So, how you graph this one? Since the y-intercept is 3, your starting point is 0, 3.
Alright,
And because the slope is negative 2,
where are we going?
you're basically moving over 1, like if x is 1,
Uh-huh.
you plug in 1 for x, and it would be negative 2 plus 3, which would be 1. So you would go over 1 down to 2, 1 there.
Good.
Now draw a line. And it's straight.
Looks good to me.
Alright. The next one. Someone help me out. What do I do? I'll grab this.
How you start at 3?
Alright, so we're gonna start at 3.
A y-intercept of 3. Now what?
And just one,
Just one.
one,
Which way?
right one, and
Right one,
up
and then up one. Right one, up one. Right one, up one. Just by looking at that first equation, what do you know about the line?
It's negative.
Yeah, it's negative. So what does that tell you? The slope is negative. What does that tell you about the line? What's it gonna look like?
It's just
Going down.
Yeah, it's going down. Negative slope. The line's decreasing. All right. So what do we know? Can we find a solution? Is there a solution?
Yes.
All right. What's
So,
how
like the last one, they had the same slope. For this one, they don't have the same slope.
all
But
right.
the only thing that's in common with them is their y-intercept. And because the y-intercept is the same and they're starting from the same starting point, there is a solution, and the solution is 0, 3. Because it's the only point they cross.
Do they need to share a y-intercept for there to be a solution?
what you mean?
Do they need to have the same y-intercept for there to be a solution? No. What's really telling us there is a solution? The fact that they have what? Different, I heard someone say, I think Leo said. Different slopes, that's key. Could we prove that 0, 3 is the solution here? How would you prove that 0, 3 is a solution to both?
Maybe you can fill in what it is for 0 on both functions and so you can see an answer.
So if the coordinate 0, 3 is a solution for this system, what do I know about an x of 0 and a y of 3? What will it do to both equations? Like if I plug in x is 0 and y is 3 in the top equation, and then I do x is 0, y is 3 in the bottom equation, what will I get for both?
The same information.
Both equations are what?
What do we got for the first one? When x is 0, y is 3. What do we got? 3.
3 equals 3, which is what? That equation, that coordinate makes the equation. Just talk about the first one. If those values make the equation equal on both sides, we know that it's what? Let's back up. Someone say it. How do you know that x of 0 and y of 3 works for the first equation? How do we know? How did we just prove it? We substituted in an x of 0 and a y of 3, and what do we see? If that said, instead of 3 equals 3, it said 7 equals 3, what do I know about the coordinate? We're trying to prove that 0, 3 is the solution to the system. In order for it to be the solution to the system, what must it also be the solution to? Well, the lines cross. We talked about before what the crossing line means. What does the crossing line mean, that intersection?
What did you all write down? Being in class, you all wrote down.
To solve the system.
All right, so we need to find an ordered pair that solves the system. care. You can see it on the graph. You know the solution to that system of equations is when x is 0 and y is 3. How do we know by looking at the graph?
By looking at the graph, it's where both lines are.
It's where the lines cross. If I wasn't given the graph and I was just given the two equations, how would I prove that x of 0 and y of 3 is the solution to the system?
By plugging in like you have the equation and you have x and y.
Okay.
If you want to figure out how 0, 3 is the solution, plug in 0 for x and 3 for y in both equations.
What would happen?
And what will happen to both equations if you plug in an x of 0 and a y of 3? Who's up? That is a solution for both. There are coordinates that are going to be a solution for your top equation, but not the bottom one. The difference is 0, 3 is a solution for both. The x of 0 and the y of 3 makes both of those equations true. It doesn't matter that they're both 3 equals 3. They don't have to be identical there. What they need to show is that the equation is solved. That is a true statement when those coordinates are plugged in. We did.
So we know if it's different slopes. Substitute. Okay.
Yeah.
Forget that. You never saw that. Okay. So let's graph this system of equations. Y plus 2 equals 2x. How can we graph that?
Think about how we've graphed lines so far.
Does the equation usually look like that? Y plus 2 equals 2x.
Well, isn't it the same thing as
What is it the same thing as?
the initial value?
What can we do to make it look like the equations that we're used to?
How would you graph that? If you had y plus 2 equals 2x, how would you graph that? Everyone find two coordinates on the line. What would you do?
You can do 4, so like 4 times 2 is 8, and then 8 plus 2 would be 10. And that would be your line for
Okay, so you're saying you want to find coordinates using like a table. If x is 4, what would y have to be?
10.
If x is 4, then the right side of that equation is 8. How do you make the left side of the equation 8? What adds to 2? Y would have to be 6. So you can find coordinates,
Oh, okay.
Okay. Would be 1. So that's one way you could do it.
make a table, right? That's
Take
x is 0, y is what? X is 1, y is what? X is, so you could do that. What else could you do to that equation to graph it? What is the other way that we've graphed? What do we do our entire functions unit when we graph? What kinds of equations? What do they look like?
They look like y of equals mx plus b. Like if you have your slope, you have to include your y intercept proportional.
Okay.
So how can we take this? Y plus 2 equals 2x and make it look like that y equals mx plus b form?
How can I get that equation and put it into slope-intercept form?
Subtract 2
Why?
Why would
to
you
get
subtract
y
the 2?
by itself.
You want to get y by itself. It says y equals mx plus b. So we have the y on one side of the equation, everything else on the other.
This is actually the same thing that we did in Unit 1, solving literal equations. Right? We did some formulas, but that's a literal equation. There's two variables, you're solving for a specific variable. This is a strategy to graphing, because some of you are really good when you have an equation in slope-intercept form, y equals mx plus b, but sometimes you won't be given the equation in slope-intercept form. You may need to work it through a little bit, which you can do.
Alright, so now can we graph that easily? How can we graph it? Start where?
Negative 2.
Alright, so what point?
0, negative
0, comma negative 2 is our
2.
y-intercept. Okay, where am I going to go from there?
Right 1.
To the right one,
And out 2.
and then up 2. Our slope is 2, so we're going to go to the right one, up 2. So there's one line. Alright, distribute. You're gonna help us distribute. So what do we got when we distribute?
2x times 2.
Y equals 2x minus 2. Okay, so let's graph this one.
It's
It's the same exact thing. Same thing. Y equals 2x minus 2. Y equals 2x minus 2. We graphed it. It would be the same line. What's our solution? What's our solution for this system? Is there a solution?
yes.
What do we think? How many think yes? There's a solution. How many think no? There's no solution.
It's not a trick. Can you find one coordinate that makes that true? That is a solution to both equations?
Yeah, they are.
Say again? So what's the solution? Infinite. Yeah.
Infinitely many solutions. Okay, so if there's many solutions to a system, what do the equations have to look like? What do the slopes have to be? Yeah, they have to be the same. So the same slope. And what about the y-intercept? What about the y-intercept? What do they have to be? The same. And the same y-intercept.
Now they are not going to be identical right away. They're not going to say like y equals 3x plus 7 and y equals 3x plus 7. They will require you to do a little bit of work.
So every single point on those lines work for both of those equations. Infinitely many solutions.
I have a question about that. Would it also be all real numbers, or is that a different term?
It's not all real numbers.
Okay.
Because for that, the coordinate 5, 0 is not a solution.
Okay.
Because 5, 0 is not on either one of those lines. So what you're talking about is what's the solution for the system? There are infinitely many. There's still the coordinates on the line. But you can't generalize and say all numbers because it's not all numbers. You can see coordinates on that graph that are not a solution on that line. You know what I'm saying?
So the system has many solutions, has the same slope and the same y-intercept. Okay. We have time to do this, right? Okay. No solution. What? What is the slope and the y-intercept? No solution.
Just to summarize what we identified, because you should have this written down. These are common questions for systems. Do they have no solution, one solution, or infinite? What could you see in the equation to identify before you even graph it if there was no solution?
It's a different line.
Alright, different y-intercept. Alright, what about the slopes?
Same.
But the same slope. So no solution.
This is a really great visual, just with these three on like almost like a foldable kind of thing to have these.
Yeah, so if you write these down, this is really good. It shows you an example of equations that have no solution, a system that has no solution, and then you can write down the same slope and different y-intercept.
The reasons why they have no solution.
Alright, and then one solution, what do we know about the slopes and the y-intercept?
The key here is what?
The different.
What needs to be different for you to know that they have one solution? The slope.
Different slope.
If they could share a y-intercept, they could have the same one. If they have a different slope but the same y-intercept, what is the one solution?
The y-intercept.
The y-intercept, right? We proved it, but again, those are things that the more you work with systems, you'll kind of pick up on those.
And then what about infinitely many solutions?
If it's the same equation.
Be specific though, because
Like
it's
same
not going to be the
y-intercept.
same from the beginning.
The same slope, and what else?
Same y-intercept.
And the same y-intercept. It's a really good idea to have these examples written down so you can clearly see.
This will be put on an anchor chart, just like from Unit 1, the one solution, no solutions, and infinite solutions to an equation. We'll also have one solution, no solutions, and infinite solutions to a system of equations. We'll put that up on an anchor chart once the other class does it.
Alright, so, sorry.
by graphing them. We will advance to solving systems without graphing. The reason we start with the graphing is you just ended a unit where we worked on graphing functions. So we're extending that, and you're just bringing in that knowledge. Because you already know how to graph, it's so much more straightforward to start this way. Because that's not the you've already learned how to graph a line. Now you're going to kind of graph two together and evaluate them as a system, which is why we start with graphing. We know it's not a fan favorite. We know that it's not the preferred method to solving, but we do start that way because of the unit that you just finished.
Okay, so in your groups, I want you to graph both of these and find if it has no solution, infinite solutions, or one solution. If it has one solution, write down the solution. Okay,
You may be able to see it, but still graph it. Okay, because for those of us that are going to have to redo Unit 2 work, some of it's graphing.
Right, so graph both of these systems in your groups.
So what do you think?
Remember, the graph doesn't have to be perfect.
The second one?
Just
Prove it.
so
Graph
you
it.
can see the coordinates on it.
Okay.
Oh, did you see that?
Yeah, I got it. Want to do them during PLC?